Hi everyone, today we're going to be going over EE386 in preparation for the finals, so we're going to just get started here. So basically, we're going to be going through a lot of examples to explain the theory. So the first one is going to be determine the direct form to realization of the following LTI system. And for our LTI system, they give us here y of n is equal to x of n minus x of n minus 1 plus 2x of n minus 2 minus 3x of n minus 4. Okay. So a lot of times in this chapter, we were dealing with FAR and II, and basically when we're working with, there's two different types of forms, direct form 1 and direct form 2. We'll notice that direct form 1, you'll see that y of n is recursive, where when you're working with direct form 2, you're going to notice that y then is not recursive. And when you're also dealing with these direct form 1, you are then going to make v of n not recursive. And then for your direct form 2 here, you're going to make your omega n recursive. And we'll see where this comes into play here. This omega n and this v of n, but just know your y of n, here we see it's not recursive, so that's why we are going to, when we write it in the direct form 2 structure, we're going to notice that we don't have to take that into account. And so now that we have this material provided, we'll see that, okay, we just have x terms and we have y terms. So remember, whenever you start out, you're going to have your x of n as your input, and then you're going to get to your output y of n. So we have to look at the strategy here, going from our x of n, how are we going to get to our output? And the biggest thing about it is that all of these for output are a combination of x of n here. And so you're going to see that when we do the drawing of this signal flow, we're going to have delays, because we'll notice that x of n minus 1, x of n minus 2, x of n minus 4. So we have to have 4 delays for a total of 4 of these right here. So we have 4 the unit block delays. And then after that, notice that our x of n is just added to negative x of n minus 1. So at this point right here, it's x of n minus 1. At this point right here, it's x of n minus 2. At this point, it's x of n minus 3. Then after this block, it's x of n minus 4. Okay? And so we're going to have our x of n added right here. Then our x of n minus 1, we're going to have a subtraction block. So you're going to see this, we're going to multiply by negative 1 here, x of n, so it becomes minus x of n minus 1. Then here we're going to multiply by 2 here. So it'd be 2 x of n minus 2. And then here, notice there's no x of n minus 3, but there's a minus 3 x of n minus 4. And so what we have here, notice though the signals come in right at this point. So we're actually going to make this an adder block right here, because 2 signals are coming in. And at this point right here, there's more than 1 signal coming in. So this will also be an adder block. And so the final output, it's going to be here, x of n minus x of n minus 1 plus 2x of n minus 2, and then minus 3x of n minus 4. And so that's the direct form 2 realization for this one. Okay, so for our next one, it's going to say consider the discrete time system. And for this discrete time system, they're going to give us an input x of n, and then it's going to go through a summing block here. And then from the summing block, we're going to see there will be a delay block. And then it's going to go down back to the summing block here. And then we're going to see it's going to go to the right. And then here we're going to have our plus. And then our y then at the output. So what we're going to see here is they gave us this discrete time system here. And what we can tell is there's an input, output. So what this is going to be at this point, notice that we're going to call the point right here. It's a different signal because it's x of n, but it's going to be added with something else to produce a different output. So I'm going to call this omega n because it's a different signal afterwards. There's like an intermediate signal between x of n and y of n. So I call that omega n. And so what we're going to see here is at this point, it's omega n minus 1 after the delay. And then notice here it's multiplied by 1/2, and then that's added with x of n, produce omega n. So here I can define that omega n is equal to x of n plus 1/2 omega n minus 1. Okay, that makes sense because at this point it's x of n plus 1/2 omega n minus 1. And then my output, y of n, is going to equal, well, it's omega n's one of the inputs here. And then omega n minus 1 is the other one. Okay, so from this, we want to find the directions. We're saying find the input-output relation. So now that we're given we know the output y then. And so we have to put this in terms now of our x of n in y of n on this right-hand side, because for linear constant coefficient ordinary differential equation, it's always y and x are in that equation. So we want to try and eliminate this omega somehow. So we only get it in terms of x and y. So here, what I'm going to do is I'm going to substitute in for omega n what I have up here, because I notice I can substitute in an x in here. So I'm going to rewrite y of n, set it equal to x of n plus 1/2 omega n minus 1. And then substituting in then omega n minus 1 here, that's just x of n minus 1 plus, and then 1/2 omega n minus 2. Okay, so now I'm going to group my x of n terms together, my omega n terms together. So I'm going to get y of n is equal to x of n plus x of n minus 1 plus 1/2 omega n minus 1 plus 1/2 omega n minus 2. And what we're going to notice here is if we have 1 unit delay, notice if we multiply y of n by 1/2 and have a unit delay of 1, what this is going to transform into is applying 1/2 y of n minus 1. It's going to give us 1/2 omega n minus 1 plus 1/2 omega n minus 2, which now we can substitute in. Isn't this equal right here? This part is equal to 1/2 y of n minus 1, because this is what the right-hand side of the equation is equal to. So we can substitute in for here 1/2 y of n minus 1, and then rewrite the rest of the equation, just bring down the other terms, y of n, and then plus x of n plus x of n minus 1. And that's how we format our equation for the input-output relation. So it's only in terms of our x and our y. Now that we talked about that one, it's going to ask us in the next part is it will say for part B, compute the 10 first samples of the output if the input signal is x of n is equal to delta n. Okay, so what we're going to do here is we know our y of n is given by the following. It's 1/2 y of n minus 1 plus x of n plus x of n minus 1. So I'm going to substitute in for my x of n delta n. So rewriting this equation, I'm going to get the following. Y of n minus 1 plus delta n plus delta n minus 1. Okay, so now that I have this equation, I'm going to start with n equal to 0. If I have n equal to 0, I'm going to get y of 0 is equal to 1/2 y of negative 1 plus delta 0 plus delta negative 1. So looking at this, we don't have any values before 0 defined for y, so this will just go to 0. Because y of negative 1, we don't have anything defined for, it's 0. This one, remember, the property, the unit impulse, is it only occurs at time 0. So this will evaluate to 1. So your y0 will equal 1, just because the delta function at 0 is 1. And now that we got that, we're going to look at n equal to 1. So y of 1 is going to equal 1/2. 1 minus 1 is 0, so this would be y of 0, and then plus delta 1 plus delta 0. Okay, so 1/2 of y of 0 would be 1/2 times 1, plus this term goes to 0, but this one would be 1. So y of 1 is equal to 3/2. Okay, now we're going to go to n equals to 2. Substituting in n equals 2 into the equation above, we have y of 2 is equal to 1/2 y of 1 plus delta 2 plus delta 1. Now that we have that, what we're going to see is y2 is going to equal 1/2, and then our previous answer was 3/2 y of 1. And then this term would be 0, this term would be 0 here, and so it would just be 3/4 for your y of 2. And then for your n equals 3, you're going to have y of 3 is going to equal 1/2 y of 2 plus delta 3 plus delta 2. Then we're going to notice 1/2 y2 would just be 3/8. Okay. And then for your n equals 4, you're going to get y of 4. And then you're going to pick up the pattern that it's just going to be the previous value of your y because the delta functions no longer will occur since it's not at delta 0. So this would be 1/2 of the previous value, which would be 3/16. And then as you go along, you're going to notice that n equals 5, n equals 6, n equals 7, n equal 8, n equal 9. What we're going to get is at 5, it's going to be 1/2 the previous value, so it's going to be 3/32. Then at 6, it's going to be 1/2 previous value, so it's going to be 3/64. At 7, it's going to be 1/2 the previous value, so it's going to be 3/128. At 8, it's going to be 1/2 the previous value, so it's going to be 3/256. And then at 9, it's going to be 1/2 previous value, so it's going to be 3/512. And now that we have all those values solved for y, when we write our vector, our y of n vector is going to equal, well, starting at 0, we had 1 for n equals 0. Then it was 3/2, 3/4, 3/8, 3/16, 3/32, 364, 3 128, and 3 256, and finally 3 over 512. So that's our y then vector for us. And now that we had our first 10 samples, that is the answer we have right here. Okay, so now that we determined that, how to solve those types of problems, we're going to look at an FIR filter. In for FIR filter, a really big thing here that we're going to notice with our FIR filter systems is that we're going to be working with basically how our transfer function and how we can get that transfer function from an FIR filter and looking at it in detail. So here we're going to just start with an example. Consider an FIR filter with system function. So they give us the system function here, which is h of z is equal to 1 plus 2.88 z to the negative 1 plus 3.4048 z to the negative 2 plus 1.74 z to negative 3 plus 0.4 z to negative 4. So they say sketch the direct form and lattice form realization of this filter. So in order to sketch the direct form and lattice form, what we're going to notice here is we count how many turns we have. So we start at 0, 1, 2, 3, 4. So we have 4. And you got to know that we have 4 terms. So it's going to be a to the 4 because 0, 1, 2, 3, 4. You start at 0. That's an important part. So a4z is going to equal your transfer function h of z. And so this is actually your a4z here. And you're going to notice that just copying down, you get 1 plus 2.88 z to negative 1 plus 3.4048 z to negative 2 plus 1.74 z to negative 3 plus 0.4 z to the negative 4. Now, knowing that's our transfer function, you got to remember the b4z is just written in the inverse order. So the coefficient here is going to come to the first term, and then coefficient here is going to come to the second term, coefficient here, third term, coefficient here, fourth, coefficient here, fifth term. So it's in the exact opposite order, so you're going to get 0.4 plus 1.74 z to negative 1 plus 3.4048 z to negative 2 plus 2.88 z to negative 3 and then plus z to the negative 4. So just flip-flopping our coefficients, then what we're going to notice here is our k of 4, which the k of 4, it's going to be given, it's the fourth one, right? So 0, 1, 2, 3, 4 is going to equal 0.4, that coefficient right there. So we got the k of 4, and there is a general equation that we use in order to solve for our next term. So that general equation is given by a m minus 1 to the z is equal to, and then here we have a m z minus k m b m of z all over 1 minus k m squared. Okay, so what we have here is we have our a of 4. So we need to determine the next one, which is a of 3. We're going to be going downwards. And so in order to determine a of 3, what we're going to see here is a3 of z is going to equal a4z. And so our a4z here, it's going to be, let me see if I do this, 1 plus 2.88z to negative 1 plus 3.4048z to negative 2 plus 1.74z to negative 3 plus 0.4z to negative 4. And then it's going to be minus km, which is minus 0.4. So I'm going to write that just down here because I can't fit it all on that one line. And then that's multiplied by b of 4z. And so that'd be 0.4 plus 1.74 z to negative 1 plus 3.4048 z to negative 2 plus 2.88 z to negative 3 plus z to negative 4. Okay. And then it's going to be all divided by 1 minus 0.4 squared. So here we go. So all of this will be divided by that on the bottom. So what we're going to see here is we're going to have 1 minus, and then what we're going to get for these. So 1, I notice there's a constant here. So 1 minus 0.4 times 0.4. That'd be 0.84 for my constant term here. It's 0.84. Then looking at my Z1 term, it's going to be 2.88 minus 0.4 times 1.74. We're going to get 2.184z to negative 1. Notice here at 3.4048 minus 0.4 times. And then here for my z to the 2, it's going to be 3.4048. You're going to get plus 2.04288 z negative 2. Then here for my z to 3 of 1.74 minus 0.4 times, and then my z to negative 3 here is 2.88. You're going to get, here it's going to be plus 0.588z to negative 3. Then my z to negative 4 term, it's 0.4 minus 0.4 times 1. I'm going to get 0 for the z to the 4th term, so I'm not going to include that because it's just a 0 coefficient all over, and then 1 minus 0.4 squared, I get 0.84. And so now when I solve for this, notice that I'm going to get 1 plus 2.184 divided by 0.84, I get 2.6 z to negative 1. And then here I get 2.04288 divided by 0.84. I get plus 2.432 z to negative 2. Then here I get 0.588 divided by 0.84. I get 0.7 z to negative 3. So now that I got my A3 to the Z term, I need to determine my B3 to the Z. So this is my A3 to Z. My B3 to the Z is very similar. It's literally just going to be the exact opposite for the coefficient. So 0.7 plus 2.432 Z to negative 1 plus 2.6 Z to negative 2 plus 1. Okay, so now 0, 1, 2, 3. So we're going to notice our K3 is going to equal our coefficient of that last term, 0.7. Okay. Now that I know that, I'm going to have to solve for my A2 of Z, which is going to equal my A3 of Z here. So 1 plus 2.6 Z negative 1 plus 2.432 Z negative 2 plus 0.7 Z to negative 3. Then it's going to be minus my K of M, which minus 0.7 times my B3 of Z, which is 0.7 here. So 0.7 plus 2.432 Z negative 1 plus 2.6 Z negative 2 plus 1. Okay. And now that's all divided by. And then here it's going to be 1 minus 0.7 squared. Okay. So when I do that calculation, I'm going to get 1 minus 0.7 times 0.7. I would have 0.51. And then here I have 2.6 minus 0.7 times and then 2.432. I get plus 0.8976 z to negative 1. And I have 2.432 minus, and then here I have 0.7 times, and then this would be 2.6, which I get plus 0.612 z to negative 2. Then here I have 0.7 minus 0.7 times, and then notice here, oh, sorry, I forgot, this is just a 1z to negative 3, and so here it should be plus z to negative 3. So let me just fix that real quick. Z to negative 3. Okay, and so this would be 0.7 minus 0.7 times 1. I get 0, so I have no z to the 3 term, and then it's divided all by 1 minus 0.7 squared. I get 0.51. So notice I'm going to get 1 plus then 0.8976 divided by 0.51. I'm going to get 1.76. Z to negative 1. Then here I get 0.612 divided by 0.51. I get 1.2. Z negative 2. Okay, so now I get my A2 of Z. So my B2 of Z is going to equal, flip-flop the coefficients. I get 1.2 and then plus 1.76 z to negative 1, and then plus, and then z to negative 2, coefficient and 1 in front. Now my k of 2 is going to equal coefficient last term here is 1.2. Now that I got that, my A1 of Z is going to equal A2Z, which is 1, plus 1.76 z to negative 1, plus 1.2 z negative 2, minus your km, and then times your B2Z, which is 1.2 plus 1.76 z to negative 1 plus z to negative 2, and then all over. And then here we're going to get, when we solve for this, it would be 1 minus 1.2 squared, which we're going to get here if we have 1 minus 1.2 times 1.2, 1 minus 1.2 times 1.2, you'll get negative 0.44. Then you'll get 1.76 minus 1.2 times 1.76. You're going to get minus 0.352 z to negative 1. Then here you'll get 1.2 minus 1.2 times 1. You'll get 0 for your last term, then 1 minus, and then 1.2 squared. So you'll have all this in the numerator divided by, and then in your denominator, you'll get minus 0.44. And that's going to evaluate to, well, this term would just turn into 1 minus, and then here, negative 0.352 divided by negative 0.44. You'll get 0.8 z to negative 1. So now that you got this, your A1 of Z, notice that your coefficient for your K1 is equal to negative 0. Check real quick. Would this be negative? Oh, sorry. This is a positive right here. So it's positive 0.8. Okay. Now that we solved for all of this, what you're going to notice is when we have our direct form, basically when we need to make our flow chart, because they wanted us to sketch the direct form and lattice form realization of the filter. How are we going to do that? So the direct form, what we needed to notice was basically our direct form, it deals with an input and an output, x of n and y of n. So we were given our system function, which was h of z in the beginning, is equal to 1 plus 2.88 z to negative 1 plus 3.4048 z to negative 2 plus 1.74 z to negative 3 plus 0.4 z to negative 4. So this is the output over the input. So y of z over x of z is equal to basically all this again. But what we're going to do here, 4048 z negative 2 plus 1.74 z negative 3 plus 0.4 z negative 4. Is notice we'll multiply everything by x of z, so you're going to get capital X of z plus 2.88 z to negative 1, capital X of z, plus 3.4048 z to negative 2, capital X of z, and then plus 1.74 z negative 3, capital X of z, and then plus 0.4 z negative 4 x of z. Okay, now when we take the inverse C transform, what you're going to notice is you'll get y of n is equal to x of n plus 2.88, and then this is x of n minus 1, plus 3.4048 x of n minus 2, and then plus 1.74, then this is x of n minus 3, and then here we're going to get plus 0.4 x of n minus 4. And that's just taking the inverse C transform here. Now that we have this, we're going to be able to determine the direct form. Notice that y of n is not recursive in this case. So since y of n is not recursive, we're going to go with direct form 2 structure. And so we have our input, which is x of n. And notice that our input x of n, it's going to have to go through delays because we have 1, 2, 3, 4 delays. So here are x of n. What we're going to see is we're going to have 4 delays. 1, 2, 3, 4. So this is what it will look like. And 4. So at this point, it's x of n minus 1. We have x of n minus 2, x of n minus 3, and then we have x of n minus 4 here. Okay. And now we have to sum them all together to get to our output, right? So we'll have a summing block here, and then we'll have our output y of n. So x of n minus 1, it's multiplied by 2.88. And so here, that will go up. X of n minus 2, it's multiplied by 3.4048. X of n minus 3, it's 1.74. And then x of n minus 4, it's multiplied by 0.4. Okay, so that's our direct form 2 structure. And now that we got the direct form structure, we're going to look at the lattice form. So the lattice form, when we're making this one, we're going to start with an input. So we'll have our x of n. And then at the very end, we're going to have our output. So y of n. So there's going to be a lot of intermediate steps in this one. So what you're going to see here, oops, let's just switch off. Okay. So what you're going to see here is basically for your lattice form, your x of n here, it's going to go through. We're going to have an adding block here, and it's also going to have a delay here. So why do we have this delay? So let me bring that into account, and then we're going to see, let me draw this actually a little further past it. Let me just draw the summing block just a little further. Okay, so you're going to see it's going to have this general type of structure here, where this one also goes to the next one, plus here, but we're also going to have, okay, so what we're going to have here for our z to negative 1, notice that when we wrote the equation, we're going to have, basically when we were doing all this math, we determined that we had K4, we had K3, we had K2, and we had K1. And what those are going to help us determine is when we do our lattice form, we have a reflection. So we have the input x of n, and it's going to be given to other titles. So up here it's f naught of n and g naught of n. So these two come from x of n, which feeds in, this input feeds in, and it breaks off into f naught of n and g naught of n. And so they are both equal to x of n. So, so f naught of n equals g naught of n, which equals x of n. They're both equal to the input signal. And so what we're going to see here is that when you do this reflection, it multiplies both by the k1. So this is multiplied by k1. This one down here multiplies by k1. Notice that this has a unit delay of x of n minus 1. And so this will be x of n minus 1 multiplied by, then we're going to have a k2 term here. Sorry, a k1. This is k1, k1. And so this one's going to take our x of n multiplied by k1. And so now what we're going to see here is then it goes to the next step within the filter. And so within our lattice form, this one's going to be known as f1 of n. And the bottom one down here is going to be known as our g1 of n, the output from the summing block. So this is g1 of n. And then this is going to pass through another delay, which is z of -1. And then it's going to go up. We'll see it goes to another summing, but it's going to go up to the summing block here. And this one's going to go down towards this summing block here. And it's going to multiply both by k2. Along those lines, you're going to see multiplication by k2. And then we're going to tell that our next output, basically after this summing block, is going to be given by g2 of n. It's going to pass through a delay, z -1, and go to the summing block. Up here, we're going to be able to tell that it's going to go to next summing block, but it's going to be multiplied here by k3. Now that we have the multiplication by k3, remember, within ours, we went all the way up to k4. So we're going to have to go up to k4. So here we're going to have another summing block here to then produce our output. But within this one right here, it's going to have to go through delay. And then it's going to then go through an adding block. And notice right here, it's going to multiply by k4 on each of them. And then, so we will get another output, but our term here, notice this one was f of 2 of n, sorry, and then this one was f of 3n. Then the output here is actually a f of 4n, which is just equal to y of n. And then down here, we had our g2 of n, then we had a g3 of n at this point. And then this is our g4 of n at the output of the bottom block, but we're interested in the output of the top block. And so notice this is just a lattice structure in the way it's formatted. And these K1, K2, K3, and K4 are reflection coefficients. And so you're going to see that this is going to be able to give us our output, specifically our h of z, which we're going to notice. And we take it all from this top equation here because we'll then be able to get our y of n, and then using that y of n with our knowledge of our x of n, we can rewrite that equation for y of n over x of n, take the z transform, and so we get y of z over x of z, so we get our h of z. But we're interested in the top one, so this is how you format it specifically in order to get the lattice structure. Notice that your f1 of n, if you just do the calculation from here, f1 of n is equal to x of n, and then it's going to be plus k1, and then it's going to be, isn't this just x of n minus 1? So that's how your f1 of n, your g1 of n term is going to equal, here your g1 of n is going to be your x of n, plus, and then it's going, so k1 x of n plus x of n minus 1. So that would be how you determine your G1 of n, x of n minus 1. And then you can keep going along. So your f of 2 of n is going to equal, well, coming into your f2 of n, you have f1 of n plus, and then it's k2, and then it looks like it's g1 of n minus 1. And so you'll get your f1 of n plus, and then k2 g1 of n minus 1. Then you get your g2 of n, which is equal to k2 f1 of n, and then plus g1 n minus 1. And you can keep going along and calculate all these, and then you would substitute back in for the G1 here. So you could get it all written in terms of your X and then your Y at the very output. So that's a way you could find it in order to determine your F4 of n. This is just the lattice structure to be familiar with because it's another way of drawing it out. So now that we determined that, we're going to look at the next part, which is going to be dealing with a recursive with the Y. So for number 4, it says obtain the direct form 1, direct form 2, and cascade realizations for the following causal system. And so for a causal system, we're given y of n is equal to 3/4 y of n minus 1 minus 1/8 y of n minus 2 plus x of n plus 1/3 x of n minus 1. Okay, so the big thing here to notice is that your y of n, we have it recursive here, and the input is recursive as well. So since it's the output is recursive, it calls upon previous values, we're noticing that this is an IIR filter. If it's only the x of n or calling upon previous values, then it'd be an FIR filter, but because the output is calling upon previous values, it's an IIR filter. And so for this one, in order to do direct form 1, direct form 2, what we're going to be looking at is for our direct form 1, we have it in the form y of n is equal to previous values of y of n, and then plus x of n in previous values of x of n. So it's in that format here, so we don't need to rewrite this equation. And so we're going to, so for direct form 1, we define v of n, and then v of n is going to equal the coefficient of the x of n term. So the coefficient is 1 x of n, and then plus, and then the coefficient, the next x of n term is 1/3 x of n minus 1. And then your y of n is going to equal the negative coefficient, the coefficient of your y of n minus 1. So it's 3/4. And then it's going to be y of n minus 1 plus. And then here we have a minus 1/8. So minus 1/8 y of n minus 2. And then you just add x, our v of n here, because that's all of our x terms, right? So we're just substituting in for x terms here on this part v of n. And so for that's the direct form 1, the general structure, because you're going to start out with your x of n, and then you're going to format it such that from your x of n here, you're going to then have a summing block, and at the output, the summing block is your v of n. So in order to form your v of n, it looks like you add in 1 x of n, which you do here, and you have to then run it through a delay, which we have a delay right here, x of n minus 1. And then we're going to then push through that delay. It looks like 1/3 is what we need to multiply it by. So 1/3, and then we're going to add that to the block. So it's 1/3 x of n minus 1 plus x of n. And so that's our v of n. Just right here, we satisfied our v of n equation. And then from our v of n, we're then going to have another summing block based on our output, our y of n here. So we'll have our output y of n, but our y then, notice that we have to have two blocks here because it is depending upon the previous value up to 2. So we take, basically, we have to shift it twice. And so within our shifting blocks, the first one, it multiplies by 3 over 4. And the next one multiplies by minus 1 over 8. And here would be the summing block of the two. And then it goes in here. So we would have here coming into our y ven, it's going to be v ven plus 3/4 of y ven minus 1, because at this point it's y ven minus 1, then minus 1/8 y ven minus 2. Okay, so that's our y of n. So that's how we're able to structure it in the direct form 1 structure. Now, in order to do the direct form 2, you're going to see for direct form 2, we're going to define omega n is going to equal. Okay, so what's the coefficient on the y term here? It's 3/4, and you substitute in for your y omega, and then n minus 1 minus 1/8 omega n minus 2, and then plus x of n. The rest of the terms are just x of n here. And then your y of n is going to equal, and then you're going to have your coefficient here is 1. So you'll do 1 omega n plus 1/3 omega n minus 1. So you just substitute in your x here with omega, and you just copy that down for your y of n. So that's how you set up the direct form 2. And then we're going to make, basically, our input here is x of n, and our intermediate step is going to be our omega n. So to form the omega n, we're going to see that it takes x of n as one of the inputs in order to get our omega n. And it's going to have to run through 2 delays. So here's one delay, and here's the second one. And so this is omega n minus 1 right at this point here. And here we have omega n minus 2. So here it's going to multiply it by 3/4. And then here we're going to have it multiplied by negative 1/8. And then what's going to happen is our omega n is equal to 3/4 omega n minus 1 minus 1/8 omega n minus 2, and then plus x of n. And then from our omega n here, we're going to format our y of n. So then here we're going to notice that y of n is going to equal, then it's going to actually be the summation. So here I should have a summing block. It's going to be the summing block of omega n in 1/3. So I'm going to have this multiplied by 1/3 here. I'm going to just put it below. So it'll be 1/3 omega n minus 1 plus omega n. So that's why we have y of n here. And that's our direct form 2 realization. Now that we have that, we need to do the cascade form. So the cascade form is a little different for our IIR filters. So what we're going to have here is, if we have to determine, when you're doing your cascade form, you have to put it in terms of h of z. And so here, if I have to put this in terms of my h of z, I'm going to notice that in order to get this, in terms of h of z, I need to do the transform. So it would be then y of z is equal to 3/4 z to negative 1 y of z minus 1/8 z to negative 2 y of z plus x of z plus 1/3 z to negative 1 x of z, format it in terms of y of z over x of z, which is going to equal, and then here we would have, if we collected all the y terms together, in our x, we're going to have 1 plus 1/3 z to negative 1 all over, and then our y terms, we're going to have here in the denominator, it's going to be 1 minus 3/4 z minus 1 plus 1/8 z minus 2. and then this would equal 1 plus 1/3 z minus 1. If you do the quadratic here, you get 1 minus 1/2 z negative 1, 1 minus 1/4 z negative 1. Okay. So here we have our h of z. So we solved for h of z basically from this by taking the z transform. Now that we have that, we're going to write this in terms of h1 of z and h2 of z. So I'm just going to call this here my h1 of z because you break it down into parts. This is my h1 of z, where this one over here, this pole is going to be h2 of z. So we're going to write it in cascade format. So what's going to happen is we're going to have our input x of n, and then it's going to go through h1 of z, and then it's going to go through h2 of z in order to produce the output y of n. Okay. So now what we need to do in order to produce the output, we're going to see that our x of n term here, it's basically going to be, when we do the cascade form, we're going to have our x of n, and then it's going to go through to a summing block here, where in our summing block, you're going to notice there's going to be unit delay of 1. And so within this, we're going to have two options. It's going to go 1/2 here or 1/3. Notice within my first one, this was a pole. My pole's going to the left by 1/2. My 0 is going to go to the right by 1/3. And so it's important if you have a polar 0, because that determines the direction and the sign. And so here we're going to notice when we have our 0, it goes to the right. When you have a pole, it goes to the left. Notice that it's 1/2 here where it's a positive 1/3. They're both positive. And so you have to take into account, even though this is a minus in front, because it is a pole, it's a positive actually, because we're going to the left-hand side. And then we'll have another summing block here. This one's going to be based on our h2 of z term. So this one right here, everything right here is just based off our h1 of z. And then we're making our h2 of z, which is going to be our delay right here, which is z to negative 1. And then we're going to have a 1/4, a positive 1/4. And then it's going to go up to the summing block. And so notice that this one was a pole, so that's why it went to the left, just like the other one. And because the sign is minus, it goes, we have it going to the left here, but we have a positive 1/4 here because it's a pole. So we treat it in that format. And then it's h2 is z, and then our output is going to be y here. And so that's the cascade form that we have for an IIR filter. It's a little different than the cascade form for the FIR filter, but just to be aware of that. And then the last one here is going to talk about determine the, so this is the last one, FIR filter, which is specified by lattice parameters. And so for lattice parameters, we're going to have K1 is equal to 1/2, K2 is equal to 0.6, K3 is equal to negative 0.7, K4 is equal to 1/3. Okay, so the big thing when we have to find an FIR filter and we're just given the lattice parameters, we're going to have to determine, okay, we have to go up to A4 of Z, which is going to give us our H of Z. And so we need to start out. And when we start out, remember your A naught of Z, which is equal to your B naught of Z, that's always going to equal 1. And so then here, your A1 of Z is going to equal, and then what we have is, it follows sort of a general rule. Let me just put the general rule up here. AM of Z is going to equal AM minus 1 of Z, and then plus KM, and then it's going to be Z minus 1, BM minus 1 of Z, And that's for m equals 1, 2, all the way up to capital M minus 1. So here, for your A1 of z, it's going to equal A0z. And then plus, and then your km here, if we start out with our m equals 1, it's going to be plus k1. And then it's going to be B0z. And then our m was 1, and so that's what we had right here. And then if we're going to, this is multiplied by z to negative 1. Oh yeah, I just forgot my z to negative 1, so I'm just going to put it at the back here, because remember, z negative 1, so I'm just going to insert that. And so I'm going to have here, it's going to be 1 plus 0.5 times z to negative 1. That's for my A1 of z. And so your B1 of z is going to equal, remember, the coefficients are just flipped, so it's that as your format. Okay, now that we have that, your A2 of z, we need to determine. So A2 of z is going to equal, and so it's A1 of z plus, and then here we're going to start out with our K2 of B1 of z, z to the negative 2. And so now that we have that, because that's the one we're focusing on now, A of 2. So 2 minus 1 is 1, and then here K of 2, and then B of 2 minus 1, B1. And so then Z negative, and then it's going to be Z to the negative 1 here. Oh, yeah. So then this would be Z to negative 1, my bad. And then what we're going to have here is your A1 of z is given by 1 plus 0.5 z to negative 1 plus your K2 was given to you 0.6. Your B1 of z is 0.5 plus z to negative 1 multiplied by z to negative 1. Okay, so when you solve for this, you're going to get here, this will be 1 plus, and you're going to have a z to negative 1 term. This would be 0.5 times 0.6. You're going to get plus 0.3, so it'd be 0.8 z to negative 1. Then your last one is going to be plus 0.6 z to negative 2. And then now that you have that, because 0.6 would be 0.3, wasn't it? 0.3, which would be 0.8. 1 plus 0.3 plus 0.6 z to negative 2. Yes, and so that's what we have here. Now that we have that, we're going to have to determine our next one, which is our B2 of z. Notice that this one will be exactly the same, but the coefficients are flipped, so 0.6, and then it's going to be plus, and then here we'd have 0.8 z to negative 1 plus 1. Okay, now our A3 of z is going to equal our A2 of z plus K3, and then this is going to be K3 multiplied by B2 of z, z to the negative 1. And so here we're going to have A2 of z, which is 1 plus 0.8 z to negative 1 plus 0.6 z to negative 2 plus, and then negative 0.7, and then B2 is going to be 0.6 plus 0.8 z to negative 1 plus 1 z to negative 1. Okay. Now, in order to determine this one, when you do the math, you're going to see that this would just be 1 plus, and then 0.8 z negative 1. If we have negative 0.7 times 0.6, that's going to be negative 0.42 z to negative 1 plus 0.8. You're going to get 0.38 z negative 1, 0.6. Here it's going to be added to negative 0.7 times 8, negative 0.7 times 0.8. You'll get negative 0.56 plus 0.6. You'll get plus 0.04 z to negative 2. And then this last term here, which we have 0.8 plus, oh, I forgot here, this is z to negative 2, of course. So this would be a z to -2 times z to -1, z -3. So minus 0.7 z to -3. Okay, so now we have that. Our B3 of z would just be the coefficients, but in opposite order. So it would be a negative 0.7 and then plus 0.04 z to -1 plus 0.38 z -2 and then plus z to -4. Okay, and then our A4z is going to equal our A3 of z plus, and then K4, then it's going to be B3 of z times z -1. You're going to get your A3z is 1 plus 0.38 z -1 plus 0.04 z -2 minus 0.7 z -3. Then plus K4 is 1/3, and then multiplied by B3z, which is -0.7 plus 0.04 z -1 plus 0.38 z -2, and then plus z to the negative, and then this is a 3, my bad, z -3. Okay, now that we have that, and we're going to simplify this equation, you're going to have 1 minus, and then 1 minus, and notice that here, oh, but remember, this is all multiplied by z to -1. So here, you're going to have positive 1, and then it's going to be 0.38 plus 1/3 times -0.7. You're going to get plus 0.147 z -1. And then you're going to have 0.04, then plus 1/3 times, and then the coefficient here is 0.04. And that will become plus 0.053 z -2. Your next one is going to be -0.7, and then it's going to be plus 1/3 times, and then here you're going to get a 0.38. So 0.38. You're going to get -0.573 z -3. And then your last one, you're going to get plus 0.33 z to -4 here. Okay, so now that you have your A4 term, your A4 of z is going to equal your h of z term, your transfer function. So that would be your answer for this question. It would be given by your transfer function. So that would be the FIR filter that you need to design. So that pretty much gives you a little run through of knowing what you're going to have. The main things that you saw within this were that you have the linear constant coefficient difference equation given to you. And that equation is given by y of n is equal to negative, and then it's the summation of all your y of n minus k terms, plus, and then the summation of all your b of k x of n minus k terms. So what we saw was that the recursive, when it's recursive on your input, so if it's just given by y of n is equal to, and then you have your x terms just here, b of k, and then x of n minus k. This is an FIR filter when it's just recursive on your inputs. But when it's recursive on your inputs and outputs, you're going to notice that your y of n is going to have both these terms, k equals 1, and then it's going to be recursive based on your y of n, and then it's going to be recursive also based on your x of n. And so that's pretty much it. And so that's the whole summary we have here. Hopefully that helps and gives you a good understanding behind the types of filters.